Hello students, welcome back. I am teaching a course on circuits and system, and today we will learn yet a very important topic on the Laplace, that is the properties of the Laplace transform. I have taken a reference from the Schaum series book, Theory and Problems of Signals and System, written by Schaum. So let's start with the properties of the Laplace transform. And herein I have listed certain properties, that is the different properties are linearity, time scale shifting, shifting in the S plane, time scaling, time reversal, differentiation in the time domain, differentiation in the S domain, integration in the S plane, and finally the convolution of it. Herein I have taken the signals as xt, for which its transform is x of s. x1t is a time domain signal, for which we will refer to its counterpart in the S plane as x1 of s. The third signal is x2t. The third signal is x2t, for which the counterpart in the S domain is x2 of s. Accordingly, the region of convergence are R1 and R2. So let's start with the linearity. We know what the linearity is. Linearity follows two principles. We already know linearity. It follows two principles, that is the additive and the scaling or the homogeneity. Additive means if we have signal x1t, for which the Laplace is x1 of s, then x2t, for which the Laplace is x2 of s. Then if you scale them, if you add them together, then we know the x1 s plus x2 s, which is the outcome of the Laplace of x1t plus x2t, which is nothing but y, let's say signal y or y of s. So this is the additive property of. Similarly, a scaling property says, or the homogeneity, if you multiply any signal, let's say x of t with a1 times of x1t, similarly multiplying this by a2, you get a2 times of x2t. So their Laplaces will be a1 times of x1s, a2 times of x2s, and accordingly the homogeneity will be a1 times of x1s plus a2 times of x2s when you take the Laplace, when it is scaled by a1 and a2. So Laplace of a1 x1t plus a2 x2 of t. So it follows the linearity principle. So first property is the linearity. Second is the time shifting. If you shift the time by t0, the response in the S domain will be for a signal which is unshifted, that is xt. So that means if the Laplace of x of t gives you as x of s, then if you shift it by t0, some constant, then the time shifting says Laplace of x of t, if you shift it by some amount, let's say t0, its Laplace will be e power of s minus s of t0 dot whatever was the Laplace of x of t, that is x of s, which is a unshifted signal, the Laplace of a unshifted multiplied by e power of minus st0. So for example, if you say we want to find out the Laplace of a signal for, I will write it here itself. So let me change the color with a grain and say, for example, if you take an example, so you can say Laplace of x of t minus phi will give you the answer as e power of minus s, and t is phi. So you can write 5 times of s into x of s. So it's very simple here. Similarly, if you shift in the s domain, you can see I shift the s domain s to s minus 0, then its time domain signal will be e power of s0, whatever is the shift in the s plane. So e power of s0t into x of t. Accordingly, the ROC will be whatever is the, for the signal x of t, x of s is the r, its new ROC will be r plus r real part of s0. Next property is the time scaling property. We know that if, so how simple it is, we know that if the Laplace of x of t, you know it is given by x1 or simply x of s, then if you scale t by some constant value, its Laplace will be, then the Laplace of a times of x of t, that is scaled by a, will be equal to 1 over a, absolute value of a, times the Laplace of the signal x t, that is xs. Time reversal is again a simple one. You know the Laplace of xt is given by x of s. If you reverse the time in the for the signal xt, then its Laplace is also equal to x of minus s, and ROC will be minus of r. That is, we know that x of t leads to x of s. Then if you reverse the time, then if you reverse the time x of minus t, its Laplace, let me write it since a pair, its Laplace will be x of minus s. And conversely, if given x of minus s, you can arrive at x of minus t. Then differentiation in the time domain. If the signal is given as x of t, and we know the Laplace is equal to x of s, then if you differentiate x of t, that is d by dt of x of t, its Laplace will be s time. So the, if you differentiate d by dt of x of t, then in the s plane, this will be equal to s into x of s, and its ROC contains R. Differentiation in the similarly, if xt leads to x of s time s plane x of s, and if you differentiate in the s domain, that is d by ds of x of s, then you can arrive at the in the time domain. So here in this case, differentiation in the s domain d by ds. So in that case, it is d by d of s of the signal x of s. Then this will be equal to, in the time domain, this will be equal to t into x of t, and negative of it. So what is it? If you differentiate the s domain equation, d by ds of x of s, it will give rise to a time domain equation which is equal to minus of t dot x of t, and its ROC will contain the complete ROC for the x of t signal. Similarly, the integration in the time domain. So if you integrate any signal in the time domain from say minus infinity to some time t of the signal x of t dt, this will give rise to its s domain equation as 1 by s x of s, and the ROC will be the new ROC. The new ROC will contain the intersection of the r times r and the real part of the s greater than 0, greater than 0. So again, the integration property of the Laplace, it says if you integrate a time domain signal from some limits, say minus infinity to plus some time t, its s plane equation will be 1 by s times of x of s, whereas the new ROC will contain the region which is an intersection of the r and the real part of s greater than 0. Lastly, the ninth property of the Laplace transform is the convolution. The convolution property of the Laplace transform says if you convolve two signals x1 t convolved with x2 t, then its Laplace is simply as x1 s dot x2 s. That is the convolution of x1 t convolved. This is a convolution symbol. Let me highlight it with the, so this is your convolution. X1 t convolved with x2 t will give rise to an s-plane equation which is x1 s dot x2 s, and again the ROC will contain the complete area which is an intersection of R1 and R2. So it must be memorized because these equations will again, whenever you have an equation, let's say for an RC signal which involves the integration and the differentiation as well. So for those, if you are to find out either given the equation in the time domain and to find out its equivalent S-plane, so these formulas will help you in the simplification process easily, and it also a lot of efforts will be reduced if you memorize these formulas and substitute directly. So take a note of all these properties. So let me again repeat the properties, and you can all repeat with me. The topic is properties of the Laplace transform. The following are the 9 properties of the Laplace transform. You can repeat it with me. Property 1 is linearity property. Property 2 is the time shifting property. Then shifting in the S domain. Property 4, time scaling property. Then time reversal property. Then differentiation in the time domain. Property 7, property 7 is differentiation in the S domain. Property 8 is the integration property. And lastly, property 9 is the convolution property of the Laplace transform. So that's all in this lecture. Hope you memorize these all properties, because they will be again most useful in simplifying the electrical or any other engineering problems. Thank you for watching this lecture.